Cisco or DHCP 6 from ISC and so on, they all give out the IPv6 address sequential. That makes it very, very easy if they use that. So if you find one address in an address base, just scan below, above that number, and that's it. And you know how things is with. So with a MAC address, you have the vendor ID, and the rest is a real key space you have to look for. So if you know that a company is using Dell, for example, you just scan the key space for the vendor ID of Dell for their networks. And that's just a Class A network, and Class A networks, that can easily be scanned. It just takes a few minutes, that's not that much. So this can be done easily. So combining them with the by hand pattern, not the random one where it's too bad, and the DHCP one, if we all combine them together, we might get a pretty good picture. So this is if people configure IPv6 host addresses by hand. This is what they use. 1, 2, 3, of course. Yeah? Or they use service ports, so 80 if it's a web server, for example. If they have more web servers, it could be 1:80, 2:80, or the other way around, 80:1, 80:2. Or some take the IPv4 address, 192:168, and so on and so on. And others use funny stuff like DateCafe, BootBabe, and so on and so on. Yeah? But these are actually rare, but still easy to look for. So I generated a big list of stuff people were doing by hand. I added all these ranges because this is the textbook configuration for DHCP, and every hacker knows how administrators love textbook examples. That's why you often see Cisco as a password on Cisco machines, because it's in all their example documentation. Same here. This is all from the example documentation for DHCP server, so you can be sure this is what they are using. And then I think that this is already installed from the big scan. Yeah? The big scan I did afterwards. So this here, the big green, this is where people configured by hand, or it was DHCP. Yeah? And we see this is already the majority of all the systems. The random privacy, we can't get them. Yeah? Hard DHCP or hard configurations or random configuration by hand. Yeah? If you see a pattern, you can do it manually afterwards. Yeah. But the IPv4 stuff, this is actually feasible again, if you know what the IPv4 address space. So if you combine, if you just take that and combine maybe with this, for example, you already have, well, 2/3, 3/4 of all the IPv6 addresses. So something which was not possible in the beginning, because the key space of 4 billion by 4 billion is too large, narrowed down with just a few packets and getting 3/4 of all the systems. So that made me happy. Smiley face. So DLive scanning. Yeah. So I brute for 3,000 host addresses based mainly on that here. Yeah. 3,000 possible variations of this, for example, but just the beginning, because we only need to scan the beginning here of this. 3,000 addresses. And again, scan those 7,300 decos I found alive. From, I think, 15,000 systems which were alive before, I now found 380,000. Yeah? So I saw this technique is really working. Now, if you compare the numbers, I found 8,000 networks alive. How does this work? How is it possible to find more networks alive you're scanning for? It is possible, and it's because if a system is not there or a network is not there, there's a nice router on the way telling you, oh, this is not available, this network. And I put these networks again into my scan because it was a new network I didn't know about, which is a router network, but who cares? And for my list of 3,000 host addresses, 2,780 unique host addresses were really used. So I knew this list is effective. So, and if I now see the chart, this is the good stuff, and this is the, okay, it was used only once. So, by just sending 2,000 packets, I get over 2/3 of the systems which are there. on average. And that's always the point, on average. For some networks, that might be all the systems because it's all easily configured for the host address part. For others, it might be 0% because it's all totally random. So you never know. But the average is, by this technique, 2/3 to 3/4 of all the systems. Yeah, I did some more stuff like reverse DNS entries and looking if I find more interesting unique host names I can use for DNS brute forcing. I said, okay, I find a few more interesting stuff, and so on and so on. And basically, that was the algorithm I was doing. Do the DNS brute forcing, look what comes out there, see if there is a new alive networks which can be scanned, doing the alive scans on the network, seeing if the reverse lookup of those found alive gives us again more host names, and so on and so on. And that's how the whole technique works. So I found the, let's say, ideal space of IPv6 host parts to check and the ideal list of DNS host brute forcing list. So really, what people are really using. So in conclusion, with the DNS brute forcing, you find on average 90% of the systems which are in the DNS with just 1,900 words. And with the live brute forcing, you get roughly 2/3 of the system with just scanning for 2,000 addresses. And this scan, depending on network throughput and stuff, 1 to 20 seconds. So something which was 4 billion by 4 billion unfeasible, now 66% of the unfeasible in just 1 to 20 seconds. This is way better than before. And there's still room for improvement. So if you combine the DNS stuff, the alive scanning technique, and you use a little bit of your brain, because if you see outputs, you can see patterns. For example, you look for the name server, you look for the mail server. You see different patterns, and then you can see more stuff like, oh, this is how they're doing it, and by hand you can scan for more. You get easily to 90 to 95% on average of all the servers in the target network. And this shows it's really possible. Yeah, that made me happy. But don't worry, there's more, there's more. And one night I was really bored in the hotel room. And when you're bored, what do? You read RFCs, like every good hacker. Yeah? You take a random RFC, you read through it and see if you find bugs. Yeah, it was really like that, sorry. I'm such a nerd. And I took the RFC for the multicast listener discovery protocol because I didn't look into multicast stuff at that point very much, and I was thinking, so okay, let's learn something about that so I can sleep easier. Because usually they are very dry. So, how does multicast listener discovery work? This is one of the essential things IPv6 relies on. So this is really, really, really important for IPv6 to work. So, multicast listener discovery. We have a router, which we call the master query router. The master query sends periodically, let's say every 15 seconds, a message on the network saying everybody who wants to have multicast traffic. This system, which might be a multicast DNS server, replies, hey, I'm a multicast DNS server, so please send me all multicast DNS traffic. This is how things work in IPv6. You have lots of multicast stuff. Yeah. This information, this router takes and then distributes it to the rest of the network. So whenever there is, at some point in the network, someone is saying, here, I want to send to multicast DNS, the routers know where to forward that. It's finally delivered here, and he delivers it to that server. Yeah? How this server is communicating with the other routers, this is PIM-SM, Black Magic. For this attack, we don't need to care about that. Yeah? But this is how the router knows what kind of multicast traffic is needed from that server or from other servers on this network. And they try to put a lot of effort in here that this cannot be denied in any way. And they even wrote in there, so yeah, this is secure and nothing can happen. Yeah, and I thought, no, let's see how this is true. So, once this is done, all the multicast traffic for DNS flows into that network afterwards. Okay, so I was thinking, if I spoof a done message, so spoofing a packet which looks like it's coming from A and saying done means
little research into it
because I don't want this multicast traffic anymore. Yeah? So eliminating the report message, I want this traffic, I said I don't want this traffic anymore. What should happen? Well, the router is saying, okay, it's not needed anymore, wonderful, I don't have to send the traffic in here anymore. Yeah, sadly that doesn't work. Because what happens is that the router sends again a network a message on the network. There's really nobody want multicast DNS traffic because otherwise I'm stopping sending this here. Then of course A will say again, oh, no, I still want that multicast DNS traffic. So that was not working. I was sad. Oh. Okay. So I knew first step is I have to eliminate that router. In the multicast listener discovery protocol, there can only be one query router, one master query router. And the algorithm for that is very, very easy. If your address, IPv6 address, is lower than those of the current master router, you are the master router. Yeah? Of course, I mean that's an easy way. There can't be two of the same addresses on the network. Yeah? So this is the easiest algorithm to use. Somehow you have to do it, and it's really the best solution. The problem is always, is it secure? In that case, of course, it's not. But it's really hard to secure something locally, because local means usually trusted. Well, unless you are here, for example, at Hackito, then local is maybe not so trusted or trustworthy. Okay, how we can win this? We can win this very easily. The IPv6 address is link local, so FE80. This is the IPv6 address every system has here on every interface. FE80 is the local IPv6 address every system has. So the lowest IPv6 link local address FE80 and all 0. Yeah, if you configure it, you're always the master. Very easy. My ISP, where I have my server, they also configured the link local by hand, but it's FE81 and FE82. So I can win that too if I FE80 all 0. So now I can become the master query router. I spoof a general query message FE80 all 0. Remember, all 0:0:0 can be replaced by a double colon. I send this message, and now he stops sending the query message. I can spoof the done message, and I can omit the message saying, oh, does really nobody wants to have this multicast DNS traffic? I can omit that. And things should go well now, right? I mean, I'm the query master. I said, we don't want that traffic anymore, so things should, so fairy tale happy ending, right? Yeah, there's another question. We must send this general query message here on a periodical basis. But if we do that, well, the system will say, yeah, I still want to have DNS traffic. And I would still have, again, spoof the done message. So there would always be a tiny window where multicast DNS traffic could reach that network. And that's not what I wanted. And maybe what you want as well. So I wanted to have a way to become the master router, sending the query message so that router is pleased, but this one is never answering with I want this multicast traffic. And I found a way. And the solution is a multicast MAC address. In IPv4, you know, okay, there's a broadcast MAC address, and it's all F. Yeah? There's also a multicast MAC address, and it starts with 33:33.